Hello guys, nice to see you.
Hello.
Hi, how are you doing?
Good afternoon.
Good afternoon. Okay. So I believe everyone who is interested already joined, and other people will join on the way. So first short recall about our previous discussion. So we started last time new topic on waves. So we introduced this periodic mechanical disturbance, which can spread in different mediums as a wave. So there are two most common. There is a differentiation of waves in two types, which is longitudinal, when elements of the medium, they are moving in the same direction, like parallel to the direction of propagation of the wave, and transverse wave, when the elements of the medium is moving perpendicular to the direction of spreading the wave. So we also derived wave function. So it's some function which gives the relationship between the vertical displacement. For instance, if we're talking about a wave on a string, when we have y as a function of x and t. So y is displacement in vertical direction at any x coordinate, at any distance, and at any moment of time. So if we assume wave function at some fixed moment of time, it just gives us the shape of the wave. So we also introduce some main parameters of waves, and one of the key parameter is definitely wavelength. So it means that the distance between two adjacent points with the same phase in the wave. So that defines the wavelength, and it is important parameter to consider when we describe different waves. So today we continue working with waves, and our primarily goal is to derive equation which defines the speed of spreading of propagation of mechanical wave on a string, and along, like after we are done with that, I believe we will also try to discuss in general terms the reflection and transmittance of waves at different interfaces. That's an important thing also to be considered. So I think that these are our two main topics we are going to work with during this discussion. So then let me change this screen to our slides. And speed of propagation of wave on a string. So let us maybe first consider some like model. Let us define some parameters of the string and its conditions, which from physical point of view would have impact on the speed of propagation of this wave. So first of all, let's say we have some disturbance, mechanical disturbance, we create a pulse. So let us show this pulse in some system of coordinates, which is which doesn't move with respect to the string. We have X, Y, and here we have our pulse. So let us consider here some small element of this string with a length ds, a delta s. So now, what would have an impact on spreading the, like how fast this disturbance, this pulse can spread along axis x, like on this string? So first of all, we need to consider tension in the string, because that's what will have, like, will be exerted on any small element of this string. And the larger tension, the higher will be acceleration of this element of the string. So it will respond faster to the disturbance, and obviously quite natural to assume that this pulse will spread on this string faster. So we can assume first that velocity, like this speed of spreading the wave on the string will be proportional to the tension in the string. However, what about some features of the string itself? Do you believe that properties, the materials properties of the string will have some impact on the speed of propagation of waves on this string or not? And if yes, then which property we should take into consideration? Any ideas?
It probably would affect, and I guess it would affect the motion of this S part in X direction.
Well, I didn't hear at the beginning. What did you suggest to consider? Can you repeat, please? Oh, sorry, we don't have any more connection, but so there was at the end of your statement, you mentioned about motion along axis X of this small element S. However, it doesn't happen because in this pulse, and or if it's wave, doesn't matter, we have only y direction displacement of this of any small element of the string, and that's the feature of wave, that in the direction of wave propagation there is no transfer of matter, there is no transfer of elements of the medium. However, energy can be transferred, but only energy. And then in this particular case, we have this pulse, then displacement is always of these small elements of the string is always along axis y. There's no displacement along axis x. So let us consider, in order to figure out this second parameter, let us consider the second law of motion in a form when we have acceleration is equal to force divided by mass. So we already mentioned that we kind of want, if we want increase the velocity, the speed of propagation, we want to have high acceleration that will result from higher tension, means this force. So we have force in the numerator, larger force, larger acceleration. That is clear. We also have here this mass. And obviously, if we consider, let's say, mass of this small element like delta m, the heavier this small element is, more difficult it will be to respond to this tension T in terms of accelerating. And that's why we should not operate with element mass delta m, because it's kind of parameter which depends on the length of this segment delta s. So it's not a feature of material from which this string is made and its shape. It also, in addition to that, it's also a function of the length of the segment. So we can express this delta m as the product of delta s times mu. Mu is a linear density of the string, means the weight of the unit length of this string. So what could be the like the parameters which defined it? First, it's material from which string is made. So obviously some metal string will be denser than like heavier per unit length than some plastic string or cotton string, if they have the same cross-section area, like the same radius of the cross-section. Another factor is cross-section. So it's the diameter of the cross-section, and the bigger, the thicker is the string, the heavier it will be per unit length. So these features of the like materials properties and size of the thickness of the string will define this parameter mu, which is linear density. But that is some feature of the string. It doesn't change. It doesn't matter which length of the string we take. It's uniform along all lengths. So it's a property of the string itself. So that's material, that's parameter we want to operate with. And in this case, we can say that speed of wave propagation along axis x, like when it moves on some string stretch along this axis, will be proportional to the tension and reversely proportional to the linear density of the string. So that is some physically based consideration which results us, like brings us to this proportionality. It's not explicit equation which gives us the accurate which can give us accurate speed of spreading mechanical wave along like on this string. However, we can predict that most likely it should be proportional to tension and reversely proportional to this linear density. However, in order to get accurate equation, we need to run some analytical derivations. So let us look closer at this string element. So we kind of scale it up. And here is our string element with some curvature. Let's say here is some point O, which is the center of the curvature of this string element. And this is radius of this curvature. So now, so the length of this element is delta S. Let us put here a vertical line and define this angle as theta. So now, if we consider tangent to this arc at these points, at the edges of the element, then with respect to horizontal line, they will form angle theta also. So now we have also some tension in this string, since we have just like cut it small element from a continuous string. We should consider these tension vectors from both sides. They act on the string. They are the same. Tension is uniform in the string, we assume. And in this case, since they are the same in magnitude and angles are also the same, the horizontal component, like net force, will be equal to 0, because horizontal components of these tension vectors, they will cancel each other. They are in opposite directions. However, the radial component along the radius of this curvature, let's call it FR, some radial force, this will exist, and that will comprise two components, radial components of each of these tension vectors. So we can write that the magnitude of this radial force will be 2 times T times sinus theta. Assuming now that theta is small, we remember from previous discussions that it's possible to make a simplification, say that it is closely equal to just theta. Sinus theta is close to just theta when theta is small. So in that case, we can write 2 times T times theta. Okay, so now what should be done? Let us consider that this pulse is moving from left to right. So this is from left to right with some speed v. So in order to make this element kind of more alive, let us consider one additional frame of reference, let's say some x prime y prime, which moves together with this pulse to the right with the same speed v. So in that case, since we know this element of the string doesn't move with respect to axis x, then with respect to axis x prime, it will move with speed v, but in the opposite direction. It will be from right to the left, because this mobile frame of reference is moving together with the pulse to the right. So with respect to that mobile frame of reference, it will move to the left with the same speed v, which is speed of propagation of this pulse on the string. So now, since there is some circular shape here, we could consider for this small element that the force which counterbalances this net radial force from tension, originated from tension, will be centrifugal force. And this centrifugal force will be mass of the element of this string, let's call it delta m, times centripetal acceleration. That will be delta m times v squared divided by radius of this curvature. So now we need to deal with this mass of the string element. We want to express it in terms of properties of the string, and also in terms of theta, because we will have theta here in the left side later. So we want to have in the right side also theta, so there is a chance that we will cancel it out. So how do we express length of this arc of the element of the string in terms of delta s, in terms of theta? Do you remember? We did something similar before. So if we consider theta in radians, then the product of radius times angle in radians will give us the length of the arc, which resides on this angle. So here we need to put also two theta, because theta is just half of this angle. We have theta here and theta here. If we multiply radius only by theta, we will get length of this segment, like half of it. If we want the whole length of the segment, then we need to multiply radius times 2 theta. So now if we consider that we know the linear density mu of this string, delta m is equal to delta s times mu, and that is equal to 2 times r times theta times mu. So now we have expression for this delta m in terms of theta and in terms of properties of the string. We can substitute it here and assume that we have equilibrium. So we have delta m times centripetal acceleration should be equal to this radial force originated from the tension. So in that case, we can write 2 times tension times theta equal to 2 times r times theta times mu, which stands for this mass, times v squared divided by r. So now we can cancel out this r, cancel out this 2, cancel out this theta. And what do we get eventually? We get that speed of wave propagation on a string is equal to square root of tension divided by linear density mu. So you see that we were not so far from reality in our suggestions here, that it should be proportional to this ratio. However, we couldn't predict the square root. So for that purpose, we had to run this analytical derivation of this equation. And that's what you definitely should remember, because can be useful in solving problems. However, you know how you can get it and where it comes from. The key thing which should be mentioned here, that we considered small amplitude pulse, because that comes from this condition when we substituted sinus theta with theta. So if amplitude is very high, then it would be more complicated case, and equation for the speed of propagation mechanical wave on string would be different. However, when the amplitudes are small, we can use this simple equation, which is very nice. Okay, so at this point, let us switch to the general discussion of these questions related to reflection and transmittance of mechanical waves. So let me try to share my screen. Okay, do you see my screen now?
Yes.
Yes. This PowerPoint, yeah. Okay, so let us assume such case when we have mechanical disturbance in the form of a pulse moving on a string from left to right to the edge attached to some wall. So it's firmly attached. It cannot move with respect to the wall. So if this pulse approaches the wall, then there will be some upwards force acting from the side of the rope, like of the string, on the wall. And according to the third law of motion, there will be reaction force, the counter force, which will be pointed downwards, and that will create another, like so-called reflected pulse, which will move backwards along this string. However, the key thing here that there will be phase shift. It will be in the opposite phase to the incident pulse. So if we have here, let's say, positive y displacement of elements of the string, here we will observe some negative y direction displacement of the elements of the string. So this incident and reflected pulses, they will be in opposite phases. So that is not always the case, because if the edge of the string is attached freely, so it can move up and down. So for instance, a model is some light ring around the some metal pipe. So if this pulse approaches this metal ring, the edge attached to metal ring from left to right, then it will exert some upward force on the ring. The ring is light and it's not fixed, so it will just go upward without creating this reaction force. And then when it goes down back to initial condition, it will generate reflected pulse, which will move from the right to the left. But in that case, we will not have the phase shift. So in this reflected pulse, y-axis displacement will be also positive. So that is about conditions for specifically for reflectance. But here you see that we don't have any rope from the other side. It ends. And if we have a system which consists of two ropes, but different ropes with different mu, different density, linear density. So one, let's say they are made from the same material, but one is thinner, another is thicker. So where the speed of wave propagation will be larger, in thinner or thicker? Ideas?
Excuse me, could you repeat, please?
So the question is where the speed of wave propagation will be higher, in the thinner or in the thicker string, assuming that the strings are made from the same material.
In the first string.
In the thinner string. Okay.
Yeah.
Makes sense, because the mu, like this density, linear density, will be smaller in the thinner string. However, keep in mind that if materials are different, the thinner string may still be heavier per unit length.
Yes.
Yeah, so that should be also taken into account. So now, if we have such interface where two different strings are attached to each other, then both phenomena are observed, reflectance and transmittance. And in this case, you need to be careful with defining from which side the incident pulse is approaching the interface. So let us consider two cases. If the incident pulse is approaching the interface from the side of same string, means from the side of that medium where the speed of propagation of this pulse is higher than in the second medium after passing this interface, then we have reflected and transmitted waves. A reflected wave, as similar to this case when we have fixed edge firmly fixed edge at the wall, it will change its phase. So means the reflected wave will go in opposite direction to the incident wave, and the phase will be opposite. So it will, the displacement along y-axis will be negative. However, the transmitted wave, or like this pulse, will be in the same phase as the incident pulse. And pay your attention on the amplitude. You see here amplitude is larger than amplitude in the reflected and transmitted waves. Means that we have some splitting of the energy which is transmitted by this pulse to reflected and transmitted waves. So we will discuss in details energy transfer carried by waves during our next discussion on Friday. But this should be taken into account. Obviously, the larger amplitude, we will have higher energy. And if we create two pulses from one, assuming that there are no other dissipation of energy, obviously these two pulses should possess smaller amplitudes. And if this wave, this pulse, is approaching the interface from the medium with higher speed of propagation, then the reflected wave will be in opposite phase. If we have different case, in this case we have incident pulse approaching the interface from the side of the thicker string, and means from the medium with smaller speed of propagation. Then we also get two waves which are transmitted and reflected. However, the reflected wave remains in the same phase as the incident one. Similar to this example when we have freely fixed edge of the string. And then we have some transmitted wave, which is also in the same phase as the incident pulse. So the transmitted wave is always in the same phase as incident wave. Like if we consider reflected incident and reflected pulse, then we need to keep in mind that the phase of reflected pulse will depend from which environment the interface is approached by the incident pulse. So that is important, because if we consider later some interaction between incident and reflected wave, this phase shift will play a big role. And in order to avoid misinterpretation, you should keep in mind these features. Also, as you see here, the amplitude of incident pulse is higher than amplitudes of transmitted and reflected, because we split the energy of the incident pulse in two components, transmitted and reflected. So, summarizing our discussion today, we derived the analytical equation for the speed of wave propagation on a string. We have shown that this speed is defined by two parameters. It's proportional to the tension of the string and reversely proportional to the linear density. Also, we consider such phenomena as reflectance and transmittance of mechanical waves. What is important to take with you, take message is the reflected, so transmitted wave is always in the same phase as incident wave, and reflected wave will either change or not its phase to opposite based on the side from which initial and incident pulse or wave approach the interface between two mediums. If it approaches the interface from the side with higher speed of propagation, then reflected wave will change phase to opposite. If in opposite case, we will have incident pulse approaching the interface from the medium with smaller speed of propagation, the reflected wave will remain in the same phase as the incident pulse. And obviously their amplitudes of reflected and transmitted waves will be smaller than the amplitude of the incident wave, because its energy will be split between two components.